So that is which line will be used? MOSI will be used. When master is transmitting this to slave, MOSI is used. The data in the master shift register is shifted out to MOSI pin here. So the data which is available in the master from its shift register will be shifted out to MOSI line, and it enters the shift register of the slave device through MOSI pin of slave device. Here the shift register data which is available at the master is shifted out using MOSI pin of the master, and it goes here and it is shifted, it enters into the shift register of the slave device through MOSI pin of the slave device. That is what is written here. Now, and similarly opposite. Now when the transmission is happening from slave to the master, the shifted out bits from the slave device shift register enter the shift register of the master device through MISO. So in general, the shift register of master and slave devices form a circular buffer. Now comparing this SPI to I2C. So SPI is most suitable for application which require the data transfer in streams. That is when you are sending the data in terms of bits, so stream wise. So the only limitation of SPI is that it doesn't support the acknowledgement mechanism. But I2C there was acknowledgement mechanism as we understood. Yeah, see, acknowledgement bit. In I2C there is an acknowledgement mechanism, but SPI there is no mechanism for acknowledgement. So this is the only limitation. Apart from this limitation, if we compare SPI with I2, SPI is most suitable for the applications which require the data transfer in terms of streams. So that was the second onboard communication interface, and now the next onboard communication interface is universal synchronous receiver and transmitter UART. Now the previous two were synchronous, but this is asynchronous. That means, so for synchronizing the sender and the receiver, so this will not make use of the clock cycles. Instead it uses additional bits in order to synchronize the sender and the receiver. Now this is what asynchronous form of serial data transmission. When I say asynchronous, there is no use of clock cycles here for synchronizing the sender and the receiver. It is through the additional bits. Now UART based serial data transmission does not require the clock signal to synchronize. That is what I mentioned. It will not use the clock cycles or clock signal to synchronize the transmitting end and the receiving end for transmission. Instead it uses a predefined agreement between the transmitting device and the receiving device. So predefined agreement or predefined contract will be there between the sender and the receiver. So serial communication setting, and what is that pre-agreement? So both the communicating parties will agree on the same baud rate. What is baud rate? Baud rate is the number of bits transmitted per second. Now if both should agree, so if the sender says I will be transmitting so many bits per second, say 100 bits per second, this receiver should also agree for that. No, I am ready to receive 100 bits per second. That is what is the baud rate. And then the parity. So for error checking, it uses the concept of parity. All these things you'll understand in the networks. There is parity checker and cyclic redundancy codes, all these things. That is parity. Both of them should agree on the same parity checker mechanism, and the number of start bits and the stop bits. When this is serial communication and the stream communication, the data that is sent by the sender will go serially, one after the other. Now a mechanism is required for the receiver to distinguish between the different bytes that are sent by the sender. Now for that you got to add the start bits, beginning before every byte starts, the start bit should be there, and when the byte ends, the stop bit should be there, and the flow control should also be there. So both the communicating parties should agree on all these communication settings. Now when they agree, that is what the predefined agreement, so they can communicate. So the start and stop of the communication is indicated through inserting the special bits in the data stream. That is what I mentioned. Yeah. So next, while sending a byte of data, the start bit is added first, and a stop bit is added at the end of the bit stream. Now the least significant bit of the byte follows the start bit. Say when a byte is being sent in the UART communication interface, so the byte will be added with the start bit and the byte will be added with the stop bit. So now the first bit of the byte will follow the start bit, and the last bit of the byte will be ended by a stop bit, and this gives an indication to the receiver, correct? No, this is the start of the byte and this is the end of the byte. Now if the baud rate is x, say for example bits per second, so the baud rate is x bits, but the sender is saying I'm going to send so many bits per second. This time slot available for the receiver to receive one bit is 1 by x. So 1 by x seconds, that means the receiver should be in a position to receive one bit at 1 by x seconds. Now if this is happening, then both the sender and the receiver are synchronized. So this is what is synchronizing without using the clock. So both of them are agreeing on a common settings. Now parity is enabled for communication. If parity is enabled for communication, that means just to avoid the communication errors. Now when I say communication, all communication, when one is sending the data to the other, it is all in terms of zeros and ones. When I say zeros and ones, and when they are transmitting over the communication interface, which is a physical wire or a wireless medium, there is the possibility of 0 converting to 1 or 1 converting to 0, because all zeros and ones, they are represented using the electrical signals or the voltage levels. Now because of voltage fluctuations and because of disturbances, there is a possibility of 0 converting to 1 and 1 converting to 0. So that will eventually lead to what the error data that is received by the receiver. Now in order to minimize this, we have something called as parity bit. Now the bit value is 1, the parity bit value is 1 for odd number of ones. Now when the sender is sending some data, what it will do, before sending it will count the number of ones in the data. If the number of ones in the data is odd numbers, it will add 1 bit value, one, just to make it as even number. And when the data is received by the receiver, what it will do, it will count the number of ones. If the number of ones is odd, it will check the parity bit that is attached. If the parity bit is 1, the receiver will know for sure that whatever the data it has received is correct. And similarly, when the sender is sending, when it counts the number of ones, if the number of ones are even, it will put the parity bit as 0. A parity bit 0 is appended. When the receiver receives, it will count the number of ones. If the number of ones are even, now what parity bit it expects is 0. If the parity bit is 0, then the receiver, for the receiver, it is sure that the sender has sent even number of ones, because the parity bit is 0. If you might ask me a question, what if the parity bit itself changes from 0 to 1 or 1 to 0? So that way, we cannot help that. So and for that purpose, we have more advanced error detection codes, something like CRC, cyclic redundancy codes. All that is not required to you now here. Now you are going to understand all those things in the computer networks or data communication. UART of the receiving device calculate the priority of that is what I told. Calculates the parity of the bits received and compares that with the received parity bit for error checking. If both are same, no error. If there is difference, then there is an error. Now the UART of the receiving device discards the start, stop and parity bit. These are all the additional bits which are added just for synchronization. Now when the receiver receives, it is going to discard the start bit, stop bit which is added at the end of the byte, the start bit which is added at the beginning of the byte, and the parity bit which is added in order to make the receiver check for the error. So this is what is the UART is. And for proper communication, the transmit line of the sending device should be connected with the receive line of the receiving device. How it is connected? Like this. Now this is one device and this is another device which has a transmitter and which has a receiver. So the transmitter of this device is connected to the receiver of this device, and the transmitter of this device is connected to the receiver of this device. that is how the connection should be made. When I say TDX, it's the transmitter line. When I say RDX, it's the receiver line. Now that was about the UART, which is an asynchronous onboard communication interface. I2C is synchronous, and SPI is synchronous, and UART was an asynchronous. Now one wire interface. Now again, this one wire interface in asynchronous half duplex communication protocol. Now why it is half duplex? Because the communication can happen only in one direction. So and this was developed by and it is again asynchronous because it will not use the clock. Instead, it uses the predefined agreement or the common settings between the sender and the receiver just to synchronize the sender and the receiver. And this was developed by Maxim Della Semiconductors. One key feature of one wire bus is that it allows power to be sent along the same. So since there is only one wire, so both power and data should be sent along the same wire. So one wire slave device incorporates the internal capacitor of this to power the device from the signal line. And one wire interface supports a single master and one or more slave devices on the bus. So again, there is only one single master, and one wire can have multiple buses also. Now how it's connected, here it is shown in the diagram. This is the one wire. Now you have the master and you have the slaves connected. See, two slaves are connected to this master. And every slave will be given this. A one wire device contains a globally unique 64-bit identification number stored within it. This unique identification number can be used to address the individual devices present on the bus. In this case, there are multiple slave devices. Now, the sequence of operation in the one wire with a one wire slave devices listed below. What the master will do is, first, master device sends the reset pulse on the one wire bus. So master device will send the reset signal on the one wire bus, or reset pulse on the one wire bus. The slave device present on the bus responds to this, the slave device present on the bus respond with the present pulse. Now when the master sends the reset pulse on this one wire, all the slaves which are connected to this one wire will respond to the master by sending a presence pulse to the master. Now the master knows who are all present, and using the 64-bit address, the master will go for initiating the communication. Now, as I already told, so there is a 64-bit identification number, so that is what the master uses. So master uses the 64-bit address of the slave device with which the communication is desired. The master device sends the read or write function command to read or write the internal memory or the register of the slave device. Now the master initiates the read or write data from the device to device or to the device. So that is from the device or to the device. All communication over one wire bus is master initiated. So only the master can initiate the communication. And here again, since there are many slaves connected to it, so the one wire bus is divided into time slots of 60 microseconds. That means, so to give a fair chance for all the slaves to communicate with the master, this is what is done. Now that was the one wire bus, which is again an asynchronous bus. Now the parallel interface. So this is the parallel bus, which is available for interconnecting all the components within the embedded system. Now all the previous communication interfaces, synchronous and asynchronous, what we discussed till now, so they were allowing only one bit at a time to be written to the master or to the slave at a time, but this will allow simultaneous communication. So this will allow the transmission of several bits at a time. Now with the diagram I'll explain, because I will not go much detail into this. Now this is the data bus, and this is the address bus. Now using this data bus, so you have several data bus here, D0 to DX-1. It depends on the microprocessor, the microcontroller. So many data bits can be sent simultaneously to the peripheral devices. That means you are sending, and you have the address lines also in order to select the required peripheral device with which the communication is desired, and the data lines are there, parallel data lines. So for example, if I say 32-bit microcontroller, you can send 32 bits at a time. But in the previous examples, you were able to send only 1 bit at a time. Now here you can send several bits at a time, and this is write line and this is write line. So if the master wants to read from the peripheral device, it will enable this read line. If the master wants to write something to the peripheral device, it will enable the write line. So this is what. So till now, you people understood the onboard communication interfaces. So now what we are going to discuss next is external communication interfaces, or the product level communication interfaces. And these external communication interfaces are used in order to make the embedded system communicate with the external world or the rest of the world. So these are the various examples for the external communication interfaces or the product level communication interfaces. Now RS-232C, this is I told already Kreno. So all these things you have seen. This is the RS-232 cable, using which you can make an embedded system communicate with the other embedded system or any other external device. And RS-485 is what you are seeing is this RS-485. And so this is one-to-one. RS-232C basically provides a one-to-one communication, but RS-485 will provide one-to-multiple communication. Now USB are well known. So this is what is USB, and all of you have used it. And IEEE 13994 FireWire, it's called as. This is what. And these days majority of the printers, and all, so they come with IEEE 1394 communication interface. And infrared, this is, and these are all the wireless. These are wired and these are all the wireless. Infrared, this is what the symbol I'm showing, infrared. So your TV remote works with the infrared. Bluetooth, all of you have in your cell phones. Wi-Fi, so majority of you have used. Zigbee, this is, and then GPRS, this. So these are all the wireless external communication interfaces, which will enable the embedded system to communicate with the external world, and these are the wired communication interfaces, which will enable the embedded system to communicate with the external world. Now we are going to discuss each one of these things now in detail. Yeah. So RS-232, 32C, RS-485, RS-230, yeah. They provide full duplex wired communication and asynchronous serial communication interface. Full duplex, that means communication can happen simultaneously in both the direction, and it's asynchronous, that means a clock signal is used for synchronizing the sender and the receiver. Now RS-232 was originally developed by Electronic Industry Association, that is EIA, in 1960s, and later it was extended. RS-232 extends the UART communication signal for external data communication, and UART uses the standard transistor to transistor logic and CMOS logic. So logic I corresponds to the bit value 1 and logic 0 corresponds to bit value 0 in the TTL and CMOS logic for bit transmission, whereas in RS-232 it is reverse. Now as per EIA standards, logic 0 is represented by this voltage plus 3 volt to plus 25 volt, and logic 1 is represented by minus 3 volt to minus 25 volt. Now hence in EIA standard, logic 0 is known as space and logic 1 is known as a mark. Yeah, and when I say RS-232, they two different types of connectors. One is DB9 connector. It has 9 pins, and I hope all of you have seen this in your even in your systems also. You will find RS-232 connectors. This is a DB9 connector, and this is DB25 connector, which has 25 pins. Yeah. And RS-232 is a point-to-point connection interface, as I already told. So RS-232, it provides point-to-point, one-to-one communication, one-to-one connection, point-to-point communication interface, and the device involved in RS-232 connections are this DTE, and DCE. There are two devices. One is DTE, one is called as DTE, data terminal equipment, another one is called as data communication equipment. So the data terminal ready DTR signal is activated by DTE. That means data terminal equipment is the receiver and data communication equipment is the sender. Now the signal that is activated by DTE is DTR. That means the DTE device should tell I am ready to receive, data terminal ready, when it is ready to accept the data. And similarly the DCE component, which is the sender, the data communication equipment, which is the sender, it is going to activate, it is activated by data set ready, because when the sender wants to send the data, so it should check the data set is ready, and when the receiver wants to receive the data, it should say I am ready to receive the data. This is these are the signals. DTR is one signal which is going to activate the DTE, and DSR is another signal which is going to activate the DCE. Now and apart from this DTR and DSR, there is something called as DCD also. DCD, data carrier detect control signal, is used by DCE to check whether the signal is good or not. So say a good signal is being received or not, to indicate DTE that a good signal is being received or not. So three signals: DTR, which is going to activate the DTE, and DSR, which is going to activate the DCE, and there is another signal, that is DCD, data carrier detect control signal, used by the DCE in order to indicate, in order to tell the DTE that a good signal is being received. Yeah, and then RS-232 supports only point-to-point communication. Yeah, that is what I mentioned, only one-to-one communication, not suitable for multi-drop communication. You cannot use RS-232 to send from one to many. Multi-drop is not possible. Hence, we have other things like RS-422 is another serial interface standard for EAE for differential data communication. It supports up to this 100 kilobits per second at distance up to 400 feet. And another one is RS-422. This also supports multi-drop communication. So using RS-422 and RS-485 also supports multi-drop communication. That means from one sender you can have multiple receivers. So one sender and multiple receivers. How many receivers can be there? Up to 10 in RS-422. Here only one-to-one, and RS-22 you can have up to 10 receivers, and this is what the specification of RS-422. And RS-485 is again enhanced version of RS-422, supports multi-drop up to 32 transmitting devices and up to 32 receiving devices. Here only one sender and 10 receivers, but RS-485 up to 32 can be sending and up to 32 can be receiving. So this is these are three different types. Okay, now is USB Universal Serial Bus, and majority of your using this is a wired high speed serial bus for data communication. Now it came with the first version USB 1.0 released in the year 1995, and it was created by this Intel, Microsoft, IBM and all. And USB communication system generally follows the star topology, with the USB host at the center and one or more USB peripheral devices connected to it in the form of the star topology. So now USB 2.0 can support up to 127 USB peripheral devices. Now this is what you are seeing. It's something like a central hub to which many peripheral devices are connected. Yeah, and now and again different standards for implementing USB host control interfaces. There are different standards. One is OHCI, Open Host Control Interface, and UHCI, Universal Host Control Interface. And thus USB 2.0 supports communication distance up to 5 meters. and the USB 0 or 2.0 standard uses two different types of connectors at the end of USB cable for connecting the USB peripheral devices and the host. One is type A connector and type B connector. So used for upstream connection with the host, and type B connectors are used for downstream connection, that is connections with the slave devices. Now generally the USBs which you find in the PCs and the laptop, they are of type A, because you connect slaves. So the desktop or the laptop, they act as the masters, and the device which you connect to it are the slaves. Hence it is called as type A USB connector. And usually this USB has 4 pins. Now if you have observed the USB pin properly, there are 4 pins. Now what are they? V bus, one is the carrier pin for carrying the power plus 5 volt, and D minus carrier data differential data carrier line, D plus differential data carrier line, and then 2 data lines are there, 1 ground and 1 power. Okay, so now USB supports 4 different types of data transfer. One is control, bulk, isochronous, and interrupt. Now what is control? Is used by the USB system software to query the configuration and issue commands to the USB device. So this control transfer is used by the USB system itself in order to configure and issue the commands to the USB device. And bulk transfer, this is for sending the data, block of data from